All right, FST. Hopefully I've got this microphone thing figured out now. The problem before was my hand was hitting the little internal mics on the tablet screen as I was using my hand to do my little notation things, but now I've got my hand. Look at this. It's all over the place, and hopefully this is sort of a sound test. Testing, testing, testing. I'm rubbing my hands over where I think those mics were causing problems before. Anyway, hopefully it's working now. And I feel a little bit silly. I kind of feel like this a little bit because that's kind of what I'm wearing. But anyway, back to FST. This is about probability distributions. This is actually the last section we're going to be doing in chapter 7. There is a 7-7, but we're actually not doing that one. This is the last one, and it kind of has to do with stats. You look at distribution things, and you see graphs like this, and you go, oh my gosh, we're going back to stats, and we kind of are. But it's a little cleaner than that. Probability distributions aren't so much about collecting data and making a graph tally thing like this, like we did with relative frequency diagrams, like the calculator does with relative frequency diagrams. We're going to talk about those today, but probability distributions, the only sort of new thing here, is about how you can stack up theoretical probabilities and find out, you can see a graphical representation, or talk about a function where we kind of add up the different likelihoods of different events within one great big experiment. So yeah, this first one, the one about the dice, really turns out nicely. It's a great example of a probability distribution. In a probability distribution where we're talking about the different sums that can show up on two dice, I found this graph online, and this has a little sorry, x-axis key here for the different sums. We can have a sum of 2 all the way up to 12. And here what's nice about this graphic is it has this little picture in here that shows, here are all the ways you can roll a 7 or roll an 8 or roll a 9. And then it has them stacked up in terms of their fraction and how much of the time you're going to roll each one of these things. Remember, there's only one way to roll a 12, and there are 36 total outcomes. One of the 36, and that's the height here, 1/36 of the time you should get a 12, and 1/36 of the time you should get a 2. And there's two ways to get a 3 and two ways to get 11. So 2/36 of the time, or 1/18 of the time, you should be expected to get each one of those things. On up to the most popular one, which is for a sum of 7, you can get that 6 out of 36 of the times, and here's the picture of that. So this kind of diagram is called the graph of the probability distribution. Okay, we did this kind of thing in the ProbSim app. I'm going to show you one of those a little bit later. We did the ProbSim app for rolling two dice before on the calculator, but we're going to use it for dice here in a second. Actually, I will talk about this for a second. Here's the probability simulator app running on the TI-84 on my computer, and I've rolled the dice here. You can see about it'll be about 200 times here. And with this graph, this is the relative frequency. We talked about this a few days ago. This is different than probability distribution. It's kind of the same in terms of what they use for scale and what the bars mean and that kind of thing. But this, notice, okay, there's this random number generator in the calculator processor here that's causing these random events to happen, or seemingly random events to happen, and it's rolling the dice hundreds of times here. I'll be up to 250 here pretty soon. And what it's doing is it's keeping a tally mark sort of for every time there's a certain sum, and you can see the shape of this graph here. It looks like I'm really unlucky with my 3s for some reason. It's just really not rolling 3s nearly as much as it's supposed to for everything else. The 3s are kind of bizarrely unlucky. But it's keeping the relative, it's called relative frequency. It's giving the relative sort of occurrences for all these things. Notice the 7 has got the highest bar, which it's supposed to have. I've had 7s more than anything else, and I've had an 8 here about, I don't know, 3/4 as often as I've had a 7. And I've had a 6 maybe, I don't know, 4/5 as often as I've had a 7. And that's kind of how this works. It doesn't give you a scale here on the y-axis, but it's just about relativity here, that the 7 is the most popular, and this little 12 bar here is this sort of fraction of that, and all the other bars are in comparison to that. And basically for the rest of this graph, everything looks pretty good. Everything looks as expected except for 3s. I'm getting this really weird jump here at 3. One of the theories about probability though is if I roll these dice and run this experiment long enough, this will look exactly like the graph on the other page that I just showed you of the relative frequency. Okay, 3 is starting to catch up with 2s there a little bit. It's going to start to show the actual relative frequency where 6 and 8 should be equal, and 5 and 9 should be equal all the way down the line. Probability distribution, on the other hand, is not about running an actual experiment and collecting data. It's about, well, this is how it's supposed to turn out. If you calculate the truly random, truly fair probabilities, this is how they stack up. There's some technical terms here in this graph. We call the x-axis here whatever we're going to be categorizing our outcomes into. Remember, there was actually 36 outcomes here, and we've kind of filtered them into these 11 categories. That was our doing. This number here, the numerical range of 2 through 12, we're going to call that the random variable. That we're going to sort the 36 values into these categories that have a number, and that's going to be the value of the random variable. Later, we're going to find the average of that kind of thing. And the y value then is just the output here, the value of the probability for each one of those things. That's why it kind of looks like a percentage here, or it can look like a fraction. Notice here also that all of these little different events, the 2, the 3, the 4, they're all mutually exclusive. And they all, if you think about the group of all of them here, this represents all possibilities for rolling 2 dice. So since these are all mutually exclusive and they all together make up a complementary set, in other words, they all always add up to everything, the area under this entire green zone here should add up to 1. If I added up 136 plus 236 plus 336, etc., that ought to add up to 36/36 or 1. And the probability function does that. It speaks to everything that's possible, and there's no overlap, and everything's mutually exclusive and can be added, and when it is added, it should add up to a total probability of 1. Okay, so your first question is, what's going to be the probability that, or sorry, sketch the probability distribution for tossing 3 coins. So we're going to put it up here. We know already how many possibilities there are for tossing 3 coins, and let's actually list them. There's not that many. The first coin could be heads or tails. Second coin could be heads or tails. The third coin could be heads or tails. We could get 3 heads. This is actually the maximum number of heads we could get on there. Let's write that down for now. But remember, there was a bunch of other possibilities. I could get heads, tails. It's going to take a second here. Heads, tails, heads. Head. This is kind of like listing the sample space like I did with the 36 dice, but there's not quite 36 this time. There's different systems you could use for how to list all these, but I'm going to use this little system. I think I have to start with tails, on the last 2. And the last coin could be heads with that, or tails. Okay, so I could get 3 heads if I did all that. These 2 possibilities I think would give me 2 heads. This would actually give me 1. I'm just counting up total heads. If this is what happened, I would have 2 heads. And gosh, can you imagine anything worse than me having 2 heads? Okay, like the Hydra. Okay, and then that would, oh, actually, sorry, that's 0. Getting a little off topic. Okay, so I could get 3 heads 1 out of the 8 times. Whoa, that's interesting. So 1 out of the 8 times I could get 3. I'll write down here. The probability that I roll 3 heads is actually 1 out of 8. The probability that I roll 2 heads is how many? Let's count them up. Out of the 8 possibilities, how much of the time could I get 2 heads? Well, there's 1, 2, 3, 4. Looks like 4 out of the 8. If I counted that one and that one and that one and that one, that's 4 out of the 8 where I get 2. Probability that I get 1 heads, that would be this one. Whoops. This one. Yeah, those are 1, 1, 1. Did I do something wrong? It's supposed to be 4. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 1, 2, 3. Oh, seriously? What did I do wrong? Oh, I know. I miscounted this one because I can. Give me a second here. This one was not 2. This one was not 2. It was only 1. So there's 3. 3 with 1. Gosh, guys, sorry about that. It's not bad enough to restart yet, but I may restart if I make more mistakes. There's 3 here with 1. That's a 1. So there's 3 here with 1. That's 1. That's 1. That's 1. Double check my count there. 3 ways to get 1. And how many ways are there to get 0? That's another possibility. You could get 0 heads. That happened here. That's 1 of the 8s. Well, luckily this adds up now. In my total number of fractions here, there's 1/8 of the time I'm going to get 0, 3/8 of the time I'm going to get 1, 3/8 of the time I get 2, and 1/8 of the time I get 3. So those are going to be my categories. Number of heads could be 0 or I did it again. 0 or 1 or 2 or 3. The most I could get would be 1 or 2. There's a possibility of, so 3/8 of the time I could get that. 3/8 of the time I could get that. And then, just to be equal here, there's really no point here at 2/8. There's nothing that happens there. But at 1/8 is when I hit the probabilities of 0 or 3. So by looking at this, what's nice about this little graphic picture then is I can see that I'm supposed to get 1 about 3 times as much as I should get 0. And I should get 1 and 2 about the same amount of time. And I should get 0 and 3 about the same amount of time. Getting 3 matching ones, I can kind of look at this really quick and go, well, 3 matching ones would have to be something like here or here. And that's not very much compared to some mixed bag. Okay. On the calculator, I can do the same thing in the probability simulator app. Let me start that up again. Go to applications here, and then jump down in the list to where we get to the letter P, which you can jump to by going alpha 8. And here we go. And I want prob sim. So scroll down until I get prob sim. And in there, hit anything. And yeah, I want to do the toss coins. I'm going to do the one I just did with the tossing of the coins. So hit OK. Remember, these are the little menu bars that go with these buttons. Right now, this is set up to just do one coin and graph heads or tails. That's not very interesting. What I care about was 3 coins. Let's just change that to 3, and then hit OK. And then here we go. And notice how it does the same thing. It counts. It's going to count these up as 0 heads, 1 heads, 2 heads, and 3 heads. Hit toss, and then if you hit toss successfully, then a bunch of coins start falling at you, and it gives you the first result here that I got 2 heads. But if I hit the plus 50, it's going to roll them 50 times automatically. And here we go. And it just starts to add those up. And look away. Already it kind of looks like short, tall, tall, short, which is kind of what I was expecting. Now it's getting a little uneven. But as I keep going, of course, theory of probability says, law of averages, all that good stuff, says that the 0 and the 3 are going to start to get really low, and the 1 and the 2 are going to be 3 times as high as those. Okay. You could do this for hours. Pretty exciting stuff. Okay, after 100, it looks like it's going to be pretty close. 0 is a little higher than 3, 1's a little lower than 2, but generally speaking, we got the right shape at least. And the last thing that they present here in 7.6, and I hope I have enough time to get through it before this video ends on me in 15 minutes, is the idea of expected value. If we're saying that, okay, here's the back to the dice. Here's the expected value for each single one. Here's the probability distribution of all those things. What should I expect on average should be my sum, should be the sum of, the average of this number. Should I expect, since I go from 2 to 12, that the average is going to be around 6, or is it going to be around 7 or 8? I don't know. Just because 7's the most likely, it's sort of the median of all the occurrences. Does that mean it's actually going to be the average number I was going to expect? So what they do, if you're going to try to figure that out, all you need to do is figure out, well, I'm going to get a 2 1/36th of the time. That should count as 2 times 1/36. It's kind of like voting for number 2. 1/36th of the people vote for 2. That kind of gets 2/36th of a point. And then I get 1/18th, or 2/36 times 3 on up. So actually for this 12, this number, since it is so low frequency, but it's a very high number, it's going to add to my average a lot more than this one. It's like saying I need to add in 12 times 1/36 for this one, to get the sort of the different weights for these different numbers and how they show up. So that written out is here. Oh, it didn't quite fit in one line. Let me fix that actually. Okay, that looks a lot nicer. Yeah, that I was going to take 1/36th of all the 2's and 2/36 of all 3, because that's how often they happen. And 7 gets added in the most because there's 6/36 of them, but these all get their vote too, relatively speaking. They don't all get an equal vote because they don't happen that much. The 12 and the 2 sort of get shortchanged. The 2 only adds to the average 1/36 of the time, and same with the 12. Anyway, it turns out with this one, if you do actually add all these up, I don't have to divide by anything because remember I'm adding little tiny fractions, really. I add them all up. The number turns out to be bigger than 1, of course. It turns out to actually be 7. 7 is the expected value. I should get... Okay, I'm going to run out of time. I'll see you at a very short part 2, I promise.